This is Project01Video01, the pencil and paper part of the project. Let's see, we got coordinate system. Call this the x-axis, this is the y-axis, and the z-axis we'll have coming out of the page and into the page in the opposite direction. We've got 4 charged particles at x is equal to 10 centimeters. They've all got the same charge, but one, that's probably not quite right, a little bit closer. So they're 10 centimeters from the origin, but then each one is 1 centimeter. From the x-axis, so this distance is 1 centimeter. And I think I'll put that down as 0.01 meters. This distance same thing, 0.01 meters, and then this distance 0.1 meters. Measured along the x-axis. Let's see if I can get that looking like it's along the x-axis. Alright, then we got a charged particle. It starts at the origin. It's got a velocity in the plus x direction. And it's going to move straight along the x-axis, because each of these particles has the same charge. Call it Qs equals 2.5 microcoulombs. That's 2.5 times 10 to the minus 6 coulombs each one. So wherever the particle is, imagine it being right here, it's going to have a force exerted on it by each of these particles, and each of those forces is going to have an x component, and each of those forces is going to have a component perpendicular to the x direction. Now by symmetry, since they're all the same distance away from the axis, the force of this one, this back one, is going to be in the plus z direction. The force, the component of the force that's perpendicular to the x-axis due to this one is going to be in the plus z direction, and the component of the total force due to this one that's in the that's perpendicular to the x-axis is going to be in the minus z direction. So they're in opposite directions, and they're going to be of the same magnitude because they're both the same distance away from the x-axis and the same distance away from the particle. So those two forces will cancel each other out, and likewise for the two charged particles that are on the above and below, the charged particles that are above and below the x-axis in my diagram, toward the top of the page, toward the bottom of the page, they'll be exerting a force in the minus x direction. Those components, the components along the x direction, all add up, and the components in the other directions, the direction perpendicular to the x-axis, cancel each other out from symmetry. So that's why the particle is going to stay on the x-axis. And in discussing that from symmetry, I find I really only have to calculate the force component along the x-axis due to one of them and multiply it by 4. So I'm going to put the particle at some arbitrary position. I choose to put it to the right of the 10 centimeter position, just so that I don't have so many minus signs in the equations that I write down. It's easier to think about it that way, but the equations will be valid for everywhere along the x-axis, in particular everywhere from 0 to 0.2 meters which represents the positions of the particles, the particle that we're concerned with. So these guys are fixed. These four are fixed in space by some unshown immovable objects, and this one particle starts out with a velocity to the right, and it's only going to move along the x-axis. It's not confined to the x-axis, but given its initial velocity being in the plus x direction, and the fact that the net force perpendicular to the x-axis is going to at all times be 0, it's going to stay on the x-axis. And so it does move just along the x-axis. Now when it's here, it's going to be this distance away from any one of the charged particles. I think I'm going to work on the one that's got a positive value of y. So, and then I just have to multiply the result by 4. So if I can draw a line between, then I'm having a hard time drawing that straight line. Alright. So it's not all that straight, but I'll call this particle number 1. Q, source, they're all the same. So this black dot here is particle number 1. Here's, we'll call this RS1. RS1 vector represents the position vector of source charge. That's what the S is for. I got 4 source charges. Number 1, which I labeled this one as number 1. And this represents, call this RP. It's the position vector of the particle, the one that's moving along the x-axis. So this vector right here, from here to here, is R. I call it, I think instead of RS1, I'll just call that R1. Just so I don't have quite so many subscripts there. So let's see if I can erase that. Not erasing it so much as just scratching it out. So that's R1. I'll call it R1. And this one will then be R. From R1 to RP, so I'll call it R1P. Alright. So we've got R1P. I need that one because that's going to be the distance between this charged particle and the victim. And the victim has got charge, we call it QP, the charge of the particle, and we've got R1P. Nope, let's put it R1 plus R1P. That 1P doesn't look too legible. R1P is equal to RP. See that? R1 goes from here to here, and then RP goes from here to here. And so those two are being added together in this vector addition diagram to form RP, the position of the particle. R1P is the one I need. To get R1P, I'll just subtract R1 from both sides. This is an equal sign in here. I'm not sure that that's that obvious. R1P then is equal to RP minus R1. And RP is just the x position of our particle times I, because it's on the x-axis, whatever the value of x is for the particle that's moving along the x-axis. And R1 is, I'll call it x1 times I plus y1 times I. And for that charge particle number 1, that's going to be 10 centimeters. It's 10 centimeters along the x-axis, and then plus 1 centimeter upward. So 0.1 meters times I plus 0.01 meters times j. Meant to write a j there. No, we don't really have to work in IJK notation because the geometry is so simple here, but I choose to, especially since things aren't that clear in the diagram at the scale I drew it. So this amounts to x minus x1 times I minus y1 times j. So that's the distance from that one fixed charge particle to the particle in question. Keep in mind that if x is less than 0.1 meters, so it's to the left here, then it's still the difference between the x scalar component of the particle that's free to move and the x scalar component of the fixed particle, but this would be smaller than the 10 centimeters, so this would be negative, and we'd say it's at some position in the minus x direction. So it still works out. Everything it's just perfect, no matter where the charged particle is. Now the distance. I want the distance between that fixed source charge and my victim, because the Coulomb's law indicates that the force states that the force depends on the distance. So that's what I got to get. I need R1P magnitude. So that's going to be R1P. I can write it with an arrow and absolute value signs, or just with no decorations whatsoever, and that's the way I choose to do it. That's going to be x minus x1 squared plus minus y1 squared square root. Pure substitution into our unwritten formula for the magnitude of a vector. And then it'd be improper to write that with just the y1 in there, but it is equal. Minus y1 quantity squared is the same thing as y1 squared, so I am going to... I can't do that in the substitution step, but I can then do some algebra. That's what I like to do there. Alright, so we can consider R1P known at this stage, and now the force F1, the total force, is going to be K Q1 times QP. This is the charge of the particle that's free to move around. This is the charge of that one of those four particles, and divided by R1P squared. So I'm not going to substitute that in there at this point, but one could. Now let's take a look at that diagram. F1P is going to be away from that charged particle number 1. and it's going to be along this same line, along in the same direction as the vector r1p. So, and I need the x component of that. Well, let's write down what f1p is. I'm just calling it F1, so it's the force on particle 1 due to, no, it's the force of particle 1 on P. I think I just call it F1. They're all on particle P, so I won't use that other subscript, so just F1. And F1 vector, any vector, is equal to its magnitude, so that's this thing right here, times a unit vector in its direction. We'll call it unit vector in the direction of F1. Now, a unit vector in the direction of F1 in this case is the same thing as a unit vector in the direction of R1P. So I'll call it F1 is equal to F1 times R1P hat. Alright, so that's this times a unit vector in the same direction as R1P. So I need R1P hat. R1P hat is R1P divided by R1P vector divided by R1P magnitude. So F1 is equal to F1 times R1P. I'll call it X1P I plus Y1P J. And 1P is hard to read there. 1P and then times J, where these are generic symbols, but X1P and Y1P are already known. X1P is X minus X1 and Y1P is minus Y1. This will be divided by, I'm using a substitution method, let's make it just a little bit more obvious. That's R1P vector divided by R1P magnitude. So this is R1P. Alright, so we got the vector F1 is equal to F1 times X1P over R1P times I plus Y1P over R1P times J. Now, what we set up here was the components of the forces. There are four forces here, and the components of them perpendicular to the x-axis are going to cancel out, and the only thing that matters is the component along the x-axis. From symmetry, the x component is the same for all of them. I guess at this point, the first thing I want to do is say, well, if all that matters is the component along the x-axis, what is F1x? And F1x is the part of this, and I think I'm gonna back up a little bit. I'll write this F1 vector. I'll go ahead and multiply the F1 through. Is F1 x1 p divided by r1 p times I plus F1 times y1p divided by r1p times j. f1x then, which is what I said I needed, is just the x component of it, the scalar x component of it. In other words, whatever is multiplying I, so f1 times and fx fixed particles from symmetry. So I got to tell the reader how I arrived at this. The total fx due to all four of them is just 4 f1 x1p r1p times that's it, times nothing, times 1 if you wish. So 4 times what it is due to one of them. The total x component of the force, and in fact the total force on our victim that's moving along the x-axis, is going to be 4 times the force due to any one of them. 4 times the x component of the force due to any one of them. No, the perpendicular to x components cancel each other out. Alright, so what do we got here? I think we're in a position to apply Newton's second law. Let's say for our charged particle P, there's one net force acting to the right, and there's a corresponding acceleration to the right from the sum of the forces to the right being equal to the mass times the acceleration to the right. We have Fx is equal to the mass of our victim times the acceleration of our victim. This is the x component of the acceleration, but that's the only direction it's in, so I choose not to write the subscript. A is the same thing as a sub x. So let's see if we can do some back substitution here to say what A is. 4f1 times x1p over r1p all divided by m. So I'll call that 4f1 x1p divided by m times r1p. And now I want to substitute for f1. F1 we found to be F1 magnitude k qq over r1p squared. K q1 qp over r1p squared. Pure substitution, that's what went in for F. Everything else I keep the same for now. M times R1P. Alright, simplify that expression a little bit. I get A is equal to 4 K Q1 QP X1 divided by m times r1p cubed. And then x1p, this is just x minus x1 from up above. So let's do that substitution. I could have done the two substitutions at once, but a is equal, but I didn't. 1qp x1 minus xp, and then mr1p cubed. So the user is supposed to supply the charge of qp. K is a universal constant. Q1 was given. X1, we're going to be looking at the, that's the 10 centimeters. XP, we're studying the motion of this particle. We're going to use a bunch of different values of XP, so whatever the current position of the particle is, that's what goes in there. So that's a variable, but M is supposed to be supplied by the user, and R1P cubed. I think that's the only thing that isn't a given, or the variable that we're letting vary as we track it. So let's get rid of that. This is M. R1P, the distance from particle 1 to our victim. I just have to find it. Okay, there it is. Position of the victim minus x1. Looks like a copy error from here to here. So this is x1. And let's see, actually I think I can probably erase that. This one area anyway. Fix that up. That was supposed to be x1. There we go. Alright, so let's stick that in for R1P. X minus x1 quantity squared plus y1 quantity squared. Square root x minus x1 squared plus y1 squared, square root, and then this baby has to be cubed. So square root means to the power of 1/2 times the power of 3 is the same thing as to the 3/2. 4k q1 qp x1 minus xp, all divided by m times x minus x1 quantity squared plus y1 quantity squared, all to the 3/2. I've been using two different symbols for the position of the particle. It's xp and just plain x. So that's I think the easy way to fix that up is to put a subscript p wherever I have just plain x. So I think I talked about not doing that before. Now I choose to do it. So it's interesting. I'm using it right there. Let me, that's wrong thinking. No, xp minus x1. There we go. I think I do want to use just the symbol x. So let's see how this x1 to p came about. To me, that should be xp minus x1. Let's see where I got that. We got it in fx. x1 to p right there. Yeah, I think for R1 to p, I started using this notation right here, the x1p, and the x1p represents x minus x1. So that was a copy error. So that's x minus x1. That's perfect. I gotta fix it up here. X minus x1 here. And I think we're in good shape. Alright. Alright, we notice that this is definitely not going to be constant. Everything is known in here except for the x, and we're going to let that vary. So when the particle is at position 2 centimeters, x is going to be equal to 0.2, for instance. So it's definitely not a constant. It depends on where the particle is. So if the position of the particle is changing with time, given that it's got some initial velocity in the plus x direction, I would expect that to be the case. That means the acceleration is changing with time, so we don't have constant acceleration. That's why it's handy to use a computer. So we'll use that idea where we use tiny little time steps. And I'll say I arbitrarily fix some delta t at a relatively small number. I'll call it 0.0001 seconds, and that's something that in the computer program I can change that. If it's taken too long, I could try a bigger time step. If it seems to be giving bad results, I can try a smaller time step. And our idea is during such a short time interval, the velocity changes by such a little bit that we can say the change in position is just the velocity times the duration of the time interval. That's how much the velocity changes, or the position changes during that time interval, how far the particle moves. And the velocity, the change in velocity is just going to be the acceleration times that time interval. If I use the point is that the acceleration changes so little over that time interval that it's we can treat it as constant for that short time interval. Same thing with the velocity. So we got to imagine dividing up time into a bunch of short little time intervals. I'm going to use a counter. I'll call it n, and we'll have n start out at the value 1. And when n is equal to 1, the time is 0 seconds. When n is equal to 1, the position, call that t sub n. The position x sub n is going to be equal to 0 because it starts at the origin. When the time is equal to 0, when n is equal to 1, the nth value of a, with n being equal to 1, so the very first value of a is going to be equal to the expression that we just calculated, 4kq charge of the particle times q1 times x minus x1, which by the way is the same thing as x2, x3, x4. That's why we're able to use that factor of 4, times all divided by x minus x1 squared plus y1 squared, all to the 3/2. I'll put this as x sub n. So this is this x sub 1 corresponds to the position of the particle. I guess at some point n is going to be equal to 1, and but that x sub 1 is not the same as that. That's actually right here, n is equal to 1. This is the first position, so this is x equal to 0 of the moving particle, whereas this was always a fixed position. It happens to be the charge of one of those four, or it's the x position, the x component of the position of all four of those fixed charges. So I just want to see if I have that right. Yeah. Our x is going to be the x sub n, position of our victim, 4k q, I reverse the order, so it's not important. I do, yeah, okay, it's essentially a copy. I guess for pure substitution, should keep the order the same. So 1p. 1 p. Okay, and the velocity is v0. So that's one of the things that the user provides. They're given the mass of the particle, the charge of the victim particle, and the initial velocity, or the initial speed of the victim particle in the plus x direction. Alright, now if we bump this up, our next value of t is going to be n minus 1 times delta t. So n is equal to 2, that'll be 1 times delta t. Our next time will be that particular value. And then xn is going to be x n minus 1 plus vn minus 1. That'll be this value times delta t. So going from time 0 to time delta t, we're saying at the end of the time interval delta t, this will be wherever it was at the beginning of the time interval delta t, which for this first one was 0, plus whatever the speed is at the start of that time interval, which was v0 for this one, times delta t. So I do need to keep delta t pretty small there because I'm pretending that the velocity is constant during the entire time interval delta t at whatever it was at the start of the time interval. So I'm introducing an error here that would tend to make the value of x a little bit small. I'll calculate the acceleration for n is equal to 2 using the same formula that I had up there. I had it in a generic fashion, so where xn is, I'll be using this value. And then v will be equal to whatever it was the time before, which for n is equal to 2 would be this value, plus this acceleration Now here's my thinking here. I use the current acceleration, which would correspond to the acceleration at the end of the time interval from time 0 to time delta t, or from the previous one to the current one. And that would make the velocity just a little bit on the high side, since assuming that it's speeding up, if we're in a region where it's speeding up. So it would make it on the high side, which because at the beginning of the time interval it doesn't have that big an acceleration. So that's going to make the velocity a little bit higher than it would be. And then when I use that to get the n is equal to 3, 1, which by the way it'll be the exact same formula, 3 times minus 1 times the delta t, it'll be 2 times delta t for the next time interval, and then the same formula here, same formula here, same formula here. But keep in mind when I'm calculating x, I'm using this v, which I said was a little bit high, but since it's the previous v rather than the current v, it's not the v from this line, but rather the one from the line before, that makes it a little bit low, assuming the thing's speeding up. And so the idea is that it would seem that those two things will offset each other and give us a more accurate result. We're going to have to test the program to see if things are really working out in this business, where we choose small time intervals and pretend that the velocity is constant during the time interval and the acceleration is constant during the time interval. So our trivial thing is, x old position is just or the current position is just the previous position plus the velocity times the time, and the acceleration, essentially using the definition of acceleration, the current velocity is going to be the old velocity plus the acceleration times the time that's elapsed since it had that old velocity. Alright, so I think we've got the algebraic solution. What we've got to do now, the only thing left for the pencil and paper part, is an outline of the steps that will make the program execute. So outline of program, I'll call it. So we have to initialize some variables, or initialize constants, I'll call it. So for instance, we're using k, set that equal to 8.99 times 10 to the 9th Newton meters squared per coulomb squared. Q1 has to be initialized to was 2.5. Let's see. 2.50 times 10 to the minus 6 coulombs. Minus 6 coulombs. What else do we have? Oh yeah, x1 is equal to 0.1 meters, y1 0.01 meters. Anything else? I think if I look in this formula here, Q of the particle is going to be given, I think I left off the mass. So the mass of the particle and the initial velocity. So initialize the constants to accept arguments. Values for, what did it say? 3 arguments: mass, charge, and initial speed. QP, I think I got that one, and V0. Okay. 3. You could want to set n is equal to 1. Calculate. Yeah, set these guys equal to 0. And so set n equal to 1. Calc. There, yeah. What was the first thing? T 0. That'll be with n is equal to 1. So this is all part of that. T equal to 0. X sub n is equal to 0. A sub n equals the expression that we had for K Q1. I gotta look at it. Q1 QP. Is an M and something to the 3/2 was x minus x1 squared plus y1 squared xn. And there was an xn minus x1 here. I think that'll do it. And set v equal to v0. And then for, this is where a while loop comes in. While xn is greater than or equal to 0 and xn is less than or equal to 0.2 meters. We want to do calculate Tn. N minus 1. I think I gotta bump up N first, so yeah. I go N equals N plus 1. Tn is equal to that. Xn is equal to V. This is Vn. N minus 1, the previous one, plus, oops, nope. Xn is what X was, Xn minus 1, plus the previous speed times delta T. An is equal to the same thing we had before. Xn. All of 3 halves. And V N is equal to the old V plus the acceleration, the current acceleration, times the duration of one of those tiny little time intervals. And so do all this. Notice this is where X keeps changing. So if, for instance, the previous V is always positive, then X is just going to be getting bigger and bigger, and eventually it'll be greater than 0.2 meters, and that'll stop our while loop. And then use that subplot command to divide the page up into the 4 pieces. Plot X versus T, comma V versus T. And A versus T. It looks like I didn't say it in the handout, but you've got to plot them all on one page in a vertical column for that time interval. So make sure we'll use that subplot command for that. But that's all we got to do. So this is just an outline. It's not the MATLAB code to do it, but an outline of the program. So make sure before, if you're relying heavily on my work on this video, for instance, make sure you look at all the videos before you get done, because sometimes I'm doing this as you would do it in a sense. Admittedly, I already programmed it up once to make sure I could get it going, but if I made mistakes here, they might turn up when I do the programming, and I'll come back and fix them. So you might find corrections to this outline of the program and to my algebra. So the corrections to the pencil on paper part, so-called pencil on paper part, in a later video for this project. So you should probably watch all the videos if you're depending on my work. If you are sure you know what you're doing, then you don't have to, but you might want to watch them all to see if there are any corrections that come up for this one. Okay, we've done that. That represents the pencil and paper part. So we did the algebraic solution. Did say I had to have at least one diagram in there, and I definitely have a diagram. There's a free body diagram there, so I have two diagrams, that one and this one, and I've got both the algebraic solution and the outline of the program, just in plain terms rather than actual coding for the MATLAB commands. Alright, let's call it a wrap.